Okay, I guess with the two beeps, that means that I'm off of mute.
Yep, I have you off of mute, and you should now have presenter privileges.
Okay.
And then you can go ahead and full screen. Your presentation's already up.
All right, we'll go to the webinar overview. Let's see, the arrow keys will advance the slides.
Yep, you might have to click on the center of the presentation just to activate it. And then, yeah, your arrow key should work. If not, there's that little thing at the top where you can go to the next slide. There you go.
Okay. In this short overview, we will offer a welcome and some acknowledgments, set the stage for the webinar, then introduce our presenters. Formally welcome you to the release detection challenges posed by Biofuels Webinar. Special thanks are in order to Jacqueline Harrison, new EPIC, for starting her third year working with USD Inspector Training webinars. These webinars always prove to be excellent training opportunities for USD inspectors. We also thank the speakers, Kevin Henderson, Curt Johnson, and Gregg, for giving their time to prepare, rehearse, and present this webinar. Final thanks go to the Biofuels Webinar Planning Team, who helped with suggesting topics and speakers for this webinar. This is an excerpt from the National Workgroup on Leak Detection Evaluations website, and this excerpt shows that the workgroup is taking notice of biofuels. Please note the applicability of this third-party certification for biodiesel blends of B6 and B20 as well as B100. And as Jacqueline has introduced, our presenters are listed here today. I'll run through some biographical information. Kevin Henderson is the president of Kevin Henderson Consulting, LLC, having formed this company upon retiring from the Mississippi Department of Environmental Quality after 25 years of service. He is a professional geologist with a BS in Geology and an MS in Geological Engineering. He provides USD training through various venues and is an instructor for many organizations, including the Steel Tank Institute. He is a member of several underwriters, laboratories, technical standards panels, and the PEI committee that is currently developing RP 1200, which is recommended practices for the testing and verification of spill, overfill, leak detection, and secondary containment equipment at USD facilities. Curt Johnson has been an environmental engineer with the Alabama Department of Environmental Management since 1984 and has been in the USD compliance program since 1989. Curt's duties include the review of cathodic protection designs and tests, the writing of new and revised USD regulations, and providing technical support to the USD compliance section concerning leak detection and cathodic protection issues. Also, Curt is currently chair of the National Workgroup on Leak Detection Evaluations, which he was instrumental in forming in 1993. Curt has a BS in Civil Engineering from Michigan Technological University. And Gregg is a research scientist in the Environmental Solutions product line of Battelle and holds an MS in Environmental Health Science from the Ohio State University. She has 10 years experience in environmental research, including environmental monitoring technology evaluations and development of analytical methods for trace analyses of environmental contaminants. Her recent work includes the investigation of compatibility issues in ultra-low sulfur diesel storing and dispensing systems, as well as evaluating automatic tank gauging systems, water detection technologies when used in ethanol blended fuel service. And with that, I turn the presentation over to Jacqueline, who will turn over to our first speaker.
Okay, while I am passing the controls over to Kevin, if you are viewing the webinar today in a group, if you could just send over the chat function how many people are watching with you, or if you want to send their names, that would be great. That way we can get an accurate count of the number of people who are on today's webinar. Kevin, are you there?
Okay, I am here.
Okay, you can just hit the full screen button on the bottom left, and it's all yours.
All right. Thank you, Jacqueline. And let me start just by saying that it is a pleasure and an honor to be here today, participating in this very important discussion. I think this is of critical importance and a great deal of interest to everyone involved in the management of underground storage tank systems. So I hope that my brief comments today will be of some value to all of us in some way or another. And really what I always try to do is help people think about what we can do to make things better. And I generally do that by pointing out problems with things. I'm very good at that. So y'all bear with me while I point out some issues and problems that we have today. Hopefully it will help us think about all these things in ways that we can help solve these issues. So I'll start by just saying that essentially there are three broad topics that we will talk about related to alt fuels and leak detection. We might look a little curious to be talking about compatibility, but it is the compatibility of some of these components that are affecting our ability to detect leak detection. So we'll talk about metallic corrosion for the most part, and a little bit about elastomerics and polymers. And then the second broad topic we will mention and show a couple of examples is what generally is termed biofouling. This is the sludge and the slime that we see in some of these tanks, primarily related to diesel fuel, ultra-low sulfur biodiesel. We'll mention that in passing. Then we'll talk about detecting water ingress related to automatic tank gauging, SIR inventory, manual tank gauging. And then we'll just briefly mention precision tightness testing. I think Gregg will give us more details about water floats and detecting water ingress, so I'm not going to spend a lot of time on that. But when we say metallic corrosion, I think we all are familiar with this compatibility issue that we have with ethanol blended fuels, namely seen within containment sumps at the tanks. So this is fairly common these days. We think we've got a pretty good understanding of how this is happening, so we will discuss how this is impacting our leak detection ability. And then we will also talk a little bit about what's going on with ultra-low sulfur diesel and or biodiesel blends that are causing some of these same sort of issues with this crud, for lack of a better term. One of the things that probably has the biggest impact to me right now as far as leak detection is our mechanical and electronic automatic line leak detectors are failing, apparently as a result of not so much a compatibility issue with the leak detector itself maybe, but just corrosion in general. I think what's happening, you can see on the leak detector that's on the left-hand side of the screen is a normal one. It's fully in the tripped position. It's where it's restricting flow, and the one on the right is partially blocked open. And then if we go to the next slide, here are two others that are fully wide open, blocked open. They are unable to function. And I believe this is simply as a result of this crud and junk, these corrosion products, clogging up the plumbing, so to speak. You know, these are simple mechanical spring-loaded devices, and I think what's really happening is the corrosion product is just clogging them up. So this becomes, troubling to see this kind of stuff going on with something as fundamental as an automatic line leak detector. And then also related to line leak detectors, we have all this metallic corrosion going on within these sumps, one of the things that we have noticed is the little copper vent tube on these leak detectors is being corroded and rapidly attacked by various sources. Now you'll notice in this picture that the copper tubing is almost black. It's kind of a dark gray, black color. This is different than what we typically see as the nice bluish green copper acetate crystallized mineral that we associate with ethanol corrosion or acetic acid corrosion. I believe what's happening here is a fundamentally different phenomenon. We see this, we almost think or believe that this is a fungus growing on this copper in this environment and causing this to happen. So when we talk about this, you may be wondering why I'm spending some time on copper leak detection tubes, because they're not a big deal, right? Well, typically no, but they can be. Here is one that has corroded completely in half and failed, and you say, so what again? Well, here is so what. This was a place that was actually in Mississippi that had a 300-gallon release from a failed copper tube on a leak detector. And so there's all kinds of leak detectors out there. This particular one that caused this 300-gallon leak was an older one, the old PLD, or piston leak detector. You know, in Mississippi, we're like a lot of other people. These older systems, they may not even have a containment sump of any kind. Some of them are just buried in the sand. We have a lot of water, very high water. So if the copper tubing breaks or gets a corrosion hole in it, then what happens is, the way these things operate, they will actually suck in water. So this is a common way that water gets inside tanks. But in this case, it was actually under the sand also, and so it actually sucked in sand when it sucked in the water through this copper tubing. So when it pulled this sand into the piston of the leak detector, this particular model is kind of unique. It has a pressure relief valve that is built into the piston itself, and you can see it pointed out in the arrow there. It's a little spring-loaded valve that was just simply meant to relieve excess pressure, and that's one of the reasons that the leak detector tube is on there, is for the fuel that is released through this pressure relief valve to drain back directly into the tank. Well, because the sand got in this leak detector, propped open the pressure relief valve, and the leak detector tube was broken, whenever the pump cut on, it was just blowing gas straight out into the environment through the broken leak detector. So about 300 gallons were lost before the product started coming up through the expansion joints in the concrete. So I think you can see that, yes, this is something that we need to be concerned about. Completely disabled the leak detector again, of course, caused a 300-gallon release. So this kind of stuff needs to be looked at. Moving on to electronic line leak detectors. I've had numerous reports to me from several different people that say that their electronic leak detectors are also not passing the annual functionality test. So not everyone does annual functionality testing on leak detectors. It is a requirement here in the state of Mississippi and some other states. So we're starting to see some of these fail the annual test, and when we take these things out and look at them, the best we can tell, the problem is, again, they are essentially plugged up by all this corrosion crud that is coming through the system. So once again, more corrosion products causing problems with the functionality of these devices. And then everyone knows that aluminum is not compatible, quote, compatible with ethanol. So here's a picture of a automatic tank gauging probe that has been corroded by ethanol, apparently, and there's a question mark here because I don't know specifically what caused this probe to be corroded, but it was in an ethanol blended tank, so I can sort of make a connection, but I can't definitively say this is what caused it. But this kind of stuff happening to a tank gauging probe doesn't look good for whatever reason. Then, not directly related, of course, to our leak detection equipment, but sort of indirectly in a way, a shear valve will prevent a leak, right? If someone crashes into a dispenser, knocks it over, shear valve breaks and it trips and stops the flow of fuel even if the pump is running. So that's the fundamental intent of a shear valve. And this is in here simply to point out, again, all of this corrosion crud and junk that's being pumped through our system is causing a serious issue. Here, these shear valves are unable to pass the annual functionality test. And again, not everyone does functionality testing on shear valves. It is a requirement here in the state of Mississippi through the Department of Environmental Quality, and the fire codes have always required shear valves to be tested. So I point this out because this is a very important issue. It's a fire safety issue that is of critical importance, and people need to be aware that this is what's going on with shear valves these days. If you haven't seen this, I think you will in the near future. So then we can talk a little bit about, elastomers and polymers. We've got lots of compatibility concerns with some of these different seals and gaskets, and we've all seen the leaking meters and all of this stuff going on. So I can't, again, directly attribute this particular meter leak to an ethanol compatibility failure, but I still continue to get quite a few reports about gasket failures with not only ethanol blended fuels, but probably more so related to ULSD. Quite a few issues apparently with older gasket systems and ULSD. So we don't really have any way to detect this leak unless we happen to be lucky enough to have a containment sump under the dispenser, and we do happen to be actually monitoring that sump, then we would see this leak. But otherwise, it probably would go undetected. Okay, so moving on to the second general topic of biofouling. This has largely been related to ultra-low sulfur diesel and or biodiesel mixtures. This is a automatic tank gauging probe, obviously, again from the state of Mississippi, and this was a diesel tank, ULSD, and this was reported or discovered because the operator was continuing to sell diesel fuel, and over the course of about 3 days was quite puzzled why his tank gauge was not registering any difference in the fuel level in his diesel tank. So they called the service tech in, they came out, pulled the probes, and this is what they saw. So when a probe gets crudded up like this, this is not hard to figure out that it's does not have the same buoyancy or density that it should, and that's the water probe and the fuel probe in this picture, and it gets all this extra weight on it. It's not going to function as designed. But the other thing that was very interesting about this one was the first time I had seen this, and have not seen this again, but the way that these probes work, as you probably know, they're magnetostrictive devices. They have a little magnet that is actually installed in the float, and the little magnet moving up and down the shaft is what causes the Veeder-Root or the tank gauging system to be able to read the fuel level or the water level. So when we pulled this one out and cleaned it up, amazingly enough, the little magnet inside the float is virtually gone. So we don't know, it was not physical damage apparently. It appears to be have been attacked by some sort of corrosion issue on the magnet itself. So that one was very unique. That obviously does not lend itself to effective leak detection when you got this kind of business going on. Then the third general broad topic is, of course, water ingress. This is something that I have been talking about for several years now. I gave a presentation at the 2009 conference on this very subject, and we're still talking about it today. So water ingress with automatic tank gauging systems is something that we need to be paying a little attention to, because fundamentally these systems are very simple the way they operate. It's nothing more than a probe with these little floats on it. The product float and the water float are of different densities. The water float has a density that is heavy enough to sink in fuel but float on water. So they simply rely on a very basic operation of water that comes into the tank will collect on the bottom of the tank. If enough of it collects on the bottom of the tank, it will pick the float up, trigger the water alarm. Okay, so what does that have to do with leak detection? Well, again, my fundamental premise is that if you have a hole in the tank, then you can have a leak, of course. So in Mississippi and a lot of areas of the country, we have very high groundwater. So getting a hole in the tank does not necessarily mean that you lose product out of the tank initially. Rather, you have water ingress. Water enters the tank. So water entering the tank can mean there's a hole in it, just like product leaving the tank can mean there's a hole in it. So it's fundamentally related. Whether you get water in the tank or product out of that hole just depends on the groundwater, and groundwater does fluctuate. So I think it's important that we be able to detect water ingress quickly. So now we've got this same automatic tank gauging system that was designed for our conventional fuels. Now we've taken ethanol blended fuel, put it in the same tank with this same system. Can we rely on this system to be able to detect water ingress effectively? And of course, there's still lots of questions about this, but again, fundamentally, the concept is pretty straightforward to me. Water that enters an ethanol blended tank may or may not actually ever make it to the bottom of the tank, and if it does make it to the bottom of the tank, it will not just sit there and collect. It will mix with the ethanol in the tank. So we cannot rely on the fundamental operation that we've always relied on, and that is water does not mix with gasoline. That is no longer true. So having said that, does the water float ever float in an ethanol blended gas when it's getting water in the tank? Maybe, maybe not. And if it does, it sometimes will trigger the water alarm, and then it suddenly will just go away. And what that means to me is the water did go to the bottom for a short period of time and then mixed with the ethanol. So the operator is now left with this system that periodically might trigger a water alarm, but the water alarm suddenly just disappears and goes away. So that is sort of like the same issue we have with a lot of operators in automatic tank gauging systems and alarms. An alarm happens, they're so accustomed to these alarms going off that they sort of just ignore them. The little boy who cried wolf one too many times. So here's another scenario where we get that same kind of business going on. So people have been trying to address this various ways. We all have probably heard and seen a lot about this. And then phase separation occurs where we don't have time to go into that. I think everybody understands what phase separation is. And we do have a system out now that is able to detect phase separation, but it's kind of almost too late at that point to me. We need to be able to detect water ingress coming into the tank before we get enough water in the tank to cause phase separation. So we can apply this same water ingress problem to simple leak detection methods like inventory control or SIR or manual tank gauging, because all of these are required and rely on the ability to detect water ingress into the tank also. So we have traditionally done that with nothing more than a gauging stick and some product and water finding paste on the stick. So anyone who has done this in ethanol blended fuels, even with the new formulated water finding paste, can find that this can be quite tricky. It's a little tricky to interpret the results, and it's just not as straightforward as it used to be. So no matter what you're doing, detecting water ingress into these ethanol blended tanks has become a little problematic, causing us to question our ability to detect a hole in the tank that's allowing water into the tank. And then finally, this thing about water ingress, we talk about the ultimate in leak detection systems, and that is a precision tightness test. Has the lowest threshold, a 0.1 threshold, 0.1 gallons per hour. So this is like the ultimate, right? But most of the tightness testing that is done these days is done with some fairly straightforward systems that rely on a water sensor placed at the bottom of the tank whenever there is water on the outside of the tank. So if you do have groundwater above the bottom of the tank and you happen to have a single-walled tank, then these systems rely on a water sensor that is physically placed at the bottom of the tank. And so I think you can see from that the implication is obvious again, that we are relying on water that enters the tank to go to the bottom of the tank and sit there and collect to give the water sensor the opportunity to discover this leak. So this raises a whole host of issues when you have groundwater to deal with in single-wall tanks. Namely, again, I believe that if we are going to claim to be able to detect a 0.1 gallon per hour leak from the tank, then that means we have to be able to detect a hole in the tank that is equivalent to 0.1 gallons per hour. Whether that hole lets water into the tank or whether it lets fuel out of the tank is almost irrelevant to me. A hole is a hole. We should be able to detect it. So there's a little bit of a debate here about what's going on, what does it mean. The protocol does not adequately address this as it is written, and as Ann will probably tell us, the protocols are being evaluated with the hopes of making them better and changing this so that we will be able to require that a tightness test be able to detect a 0.1 gallon per hour ingress of water. And in my opinion, if it's not able to do that, then it simply is not a true precision tightness test. All right, that is really all I have. Very brief, very short, and that's it. Thanks, Jacqueline.
Yep, we have plenty of time for questions. If you want to enter them into that chat box. While we're in full screen, if you hover your mouse towards the top of your screen, a little drop-down menu will come down, and the chat function is on the right, this little speech bubble. You can just click on that. Okay, just wait a few more seconds here and see if anyone has any questions. We can always come back for questions at the end of the webinar as well. Okay, we got a question here. Hold on one second. Okay, Terry, I'm taking you off of mute. Are you there?
Yes. Can you hear me?
Yes, I can.
Okay. Yes, my question was what system can now detect phase separation? Kevin said we had a system now that could detect that.
You there, Kevin?
I am here, Jacqueline. Yes, and I just wanted to take a moment. We don't mind mentioning trade names, obviously, right? So not endorsing anyone, of course, but the system that I am familiar with is made by Veeder-Root. It's called their Phase 2 float, and what it essentially is two separate water floats at the bottom of the tank. One has a density that will float in water. One has a density that will float in phase-separated material. So it is capable of detecting phase separation in the bottom of the tank.
Okay. We have another question from Mike. Let me find him here on the list. Mike, do you have a microphone? Are you there? Okay. Mike's question is, any anecdotal cases that show the difference in corrosion in E85 UST systems compared to similar E10 systems?
Yeah, that's a good question, Mike. That's, I haven't been able to make any direct connection, but man, I have seen some really, really ugly looking sumps that were E85, and I've seen some E85 sumps that didn't look so bad. And I've seen the same with E10 fuel. So it's really hard for me to make a direct correlation. I think obviously the more ethanol we have in a system, the greater the potential for the generation of acetic acid. So I think if the conditions are right, you can expect more corrosion from an E85 system than you would from an E10, just to speak in general terms.
Okay, we have another question from Wayne. He also does not have a microphone. With all the problems that were just illustrated, shouldn't the government realize by now that ultra-low sulfur diesel and especially ethanol are really failing ideas that need to go away?
Wow, I am not even going to attempt to address that question. That is not for me to say, and you know, we can debate that all day long, and I'm just not going there. Thanks.
Okay. We have a question from Aaron. Are you there? EPA Region 4.
Yeah, this was from Ben Singh. He wanted to know about the biofouling that's shown on the ACG probe. Is this a result of the microbial corrosion of the magnet?
Is the magnet failure as a result of microbial corrosion? And I do not know the answer to that. My guess would be yes, but it's hard for me to imagine what else it would be, but I don't have any definitive information regarding that. So that's my guess, but I can't say for sure.
Prove that it is microbial corrosion. So that's it. If anybody consider doing that, and if so, then we simply ask some sort of inhibitor to, from the fuel manufacturers, same way how we have anti.
Is there a follow-up question from EPA Region 4?
Yeah.
Ben, we can't hear you, ma'am.
Yeah, we couldn't hear him.
The thing is, you can actually test for microbial corrosion. So if they run the test, and if it is, then they can add maybe some sort of additive to prevent microbial growth in the fuel itself from the manufacturer, from the manufacturers themselves or the blenders themselves. Did anybody consider doing that?
Additives are a very controversial topic in and of themselves, so I think I would just leave that alone also.
Well, in terms of the fouling, if it is microbial, they can test for it, and if it is, then obviously there's a fix for it.
There should be, yes.
Okay. Go ahead, Steve. Okay. Let me mute. All right. So, oh, actually, it looks like we lost our phone. I'm going to go on to the next question from Annette. She does not have a microphone, so I will ask the question for her. Do you think the corrosion is more due to ethanol vapors rather than ethanol liquid?
Okay, Annette, yeah, that question I think has been pretty well, the mechanism of this corrosion occurring has been pretty well defined. The Battelle report that was recently published a few weeks ago has pretty clearly indicated that most of this corrosion is occurring in the vapor space of these systems, so we feel like it is more or less indirectly, if not directly, related to vapor corrosion, vapor causing the problems, not so much liquid ethanol. And let's face it, we just don't have liquid 100% ethanol in contact with anything. What we get are these solutions which are mostly gasoline, 90% gas, 10% ethanol. So it is the vapor. Ethanol is very volatile. It will be one of the first constituents to vaporize from a gasoline ethanol mixture. And so, yeah, these vapor spaces are saturated with ethanol vapors, apparently.
Okay. We have a comment from Stephen. According to an EPA study, there's a correlation between ventilation of the sump and corrosion from E10. Do you have a comment, Kevin, on this finding?
Wow, I'm not aware of that study. I would like to see that if I could, if we could get that, a link to that posted or some information posted from you, Stephen, about what that is. That concept has been around for quite some time about if it is the ethanol vapor that is causing the problem, then we simply need to vent the ethanol vapor out of these systems. So that's become sort of an air quality issue with some people, but I think there's probably some validity to that. Obviously, if we can get rid of the ethanol vapor, I think we will see much less of this sort of corrosion, gross corrosion occurring in these systems.
Okay. He's going to send that to my email, and I will forward it to you later, Kevin, for follow-up. Okay?
Great.
All right. Tim's question was already answered. I'm going to see if... All right. We have another question from someone on the headset. I had to chime in a few minutes late without microphone. How much water is too much water in an E10 tank? Second question, once any water is measurable, should they clean out the water?
Yeah, for an E10 tank, it depends on the temperature of the fuel for the most part as to how much water it can actually absorb. But generally speaking, you're talking about 1/2 of 1% water. So in a typical, if you just took 10,000 gallons of gasoline that was E10 blend, you could dissolve 50 gallons of water before you would reach the saturation point and have phase separation occur. And the second question then would be, I think obviously if you can actually measure water, freestanding water in the bottom of a tank, although theoretically that is not possible in an ethanol blended tank, what you would get would be some sort of solution mixture of ethanol and water combined. But if you were able to measure that, whether you want to call that phase separation or water or whatever you want to call it, then obviously that should be removed immediately and to the greatest extent possible.
Okay, thank you. That was the last question I have for Kevin, but he will be sticking around. So if you have questions that come up later, he will certainly be back on after the webinar to answer any more. So thank you, Kevin.
Thank you.
Okay, let me just find Curt. Curt, are you there?
I am here.
Okay, let me pass you the presenter ball.
Okay.
Perfect.
All right. We're ready to go?
Yep, ready to go.
Okay. All right. Okay. Yeah, I'm Curt Johnson, and I think the introduction by Michael was sufficient, so I won't go through all that. But I do want to thank Jacqueline for inviting me to give this presentation, and hopefully it'll be a good learning experience for all. Today I'm going to be discussing the National Workgroup Release Detection Challenges that result from the use of biofuels in underground storage tank systems and how they relate to the functionality of the release detection equipment that we list on our website. I will not be addressing the release detection compatibility issues on biofuel. I think Kevin did a great job covering that already. The National Workgroup disclaimer says, and this kind of justifies why we only address functionality, since long-term material compatibility with the product stored is not addressed in test procedures and evaluations, the NWGLDE makes no representations as to the compatibility of leak detection equipment with the product stored. I'm sure not all of you are familiar with the National Workgroup on leak detection, and it's important that you kind of understand what we're all about. So I'd like to begin my discussion with a quick summary of what we are. We have 11 members, 10 from various state UST programs, and 1 member from EPA OUST. We're an independent work group, which means we work independently from EPA and other state and local UST programs. The work group reviews third-party evaluations of release detection equipment which are performed by a third-party evaluator who tests equipment in accordance with an EPA or other acceptable test procedure or protocol. If our review of the evaluation determines that it is properly performed in accordance with an acceptable test procedure and meets EPA performance standards, then the equipment is added to our website list. This list can be found on our website at the link shown on the slide. Alabama, who I work for, of course, as well as many other regulatory authorities throughout the country, limit the use of UST release detection equipment to what is included on the National Workgroup list. All right, going to start out talking about properties of ethanol. Basically, the challenges when using release detection equipment with ethanol and ethanol blends all seem to be related to the physical properties of ethanol that differ quite a bit from physical properties of gasoline. For those of you who have had an alcoholic drink now and then, you know that water and ethanol mix very well. But I'm not sure that you know that how that mixing equal volumes of water and ethanol together will result in a slightly smaller volume than the two liquids occupied before they were mixed. This volume reduction is predictable in a lab when pure ethanol and water are mixed, but may not be as predictable in an underground storage tank when you're talking about rain or groundwater mixing with ethanol blend of E10. Also, did you realize that the more water you add to ethanol, the heavier the mixture gets? This weight is important in how it relates to the weight of gasoline. I'm going to start out with an example. Kevin already talked about this. I think I'd go into a little bit more detail on exactly the scenarios that kind of result in this. So I don't have a pretty picture like he did, but you can kind of think back on his nice picture. Okay, so what kind of potential challenges do these physical properties of ethanol create in detecting water ingress in an underground storage tank when using an ATG with a common float type water sensor? When you have a small hole develop above the bottom of an underground storage tank containing 100% gasoline and groundwater flows into the tank, the heavier water will sink to the bottom of the tank, causing both the bottom water ingress float to rise and the top product float to rise. Now, when you have groundwater ingress flowing into a tank containing an ethanol blend, you have a different behavior of the bottom and top floats, and they're not as predictable. The water, which is heavier than the ethanol blend, will sink toward the bottom of the tank, but will mix with ethanol and the ethanol fuel blend. If the water ingresses at a slow enough rate, the water may remain in suspension after mixing with the ethanol, and there will be no water at the bottom of the tank to cause the float to rise to indicate water ingress. However, the top product float will rise some, but probably not in direct proportion to the volume of the water ingress due to the small water and ethanol mixture volume decrease that I discussed on the previous slide. Typically, an ATG is not programmed to alert an operator when the top float rises. As water ingress continues and the water and ethanol mixture become heavier and heavier due to the increased amount of water in the mixture weight will exceed the weight of the gasoline and phase separate. The phase separated mixture will fall to the bottom of the tank, but as Kevin also described, will not necessarily be detected by the water ingress float, since it is not designed to float on less dense phase separated ethanol and water. As a result, there will be no indication of water ingress by the water ingress float. The product float will rise, however, but again, typically the ATG is not designed to alert the operator when the top float rises. And as Kevin discussed, some ATG manufacturers are marketing a new water ingress float that will float on phase separated water ethanol mixture to indicate a water ingress. And I would highly recommend to all of you that you would try to encourage underground tank owners and operators who market ethanol blends to replace their existing water float with these new floats during regular maintenance of their ATGs. Even when these new floats, even with the new floats, you need to be aware that there still can be a problem detecting water ingress at sites where the tanks have a high throughput of ethanol blend fuels. At high throughput sites, what I'm going to call dry ethanol is regularly being added to the tank that has the capacity to mix with what I'm going to call the wet phase separated ethanol already in the tank. The result of this may cause the weight of the ethanol mixture to decrease to where it will again be suspended in the tank. In this case, the operator may first see water ingress, but then see it disappear after delivery. So he may think the problem has gone away and he may not take any action to stop the water ingress. And I think Kevin kind of described this a little bit as well. On the next slide, I'm going to talk about a different kind of leak detection device, and it's a tank tightness test method that uses a conductivity water sensor to detect the water at the bottom of the tank when the groundwater is present outside and above the bottom elevation of the tank. This water must be calibrated by dumping several gallons of water into it, into the tank until water contacts the sensor and creates a flow of electrical current. And I don't know if I said it's a conductivity water sensor. I'll say it again because that's important. Conductivity water sensor depends on flow of electricity. So anyway, it must then be moved up slightly above the water and into the non-conductive fuel. If any water ingress occurs during the vacuum test, the water will rise, contact the water sensor, and cause a current flow, which is indicated on a meter. When ethanol is not present, you'll see either a current flow when the water sensor is in contact with the water, or no current flow when it's not in contact with the water and in contact with the fuel. However, everything changes with ethanol. When you dump water into a tank containing ethanol that calibrate the water sensor, some of the water will make it to the bottom of the tank, and some of it will mix with the ethanol and will not make it to the bottom. The water that does make it to the bottom will continue to mix with the ethanol at the interface of the water on the bottom and the ethanol fuel blend. Since ethanol alone is not conductive, but becomes more and more conductive as it mixes with water, there is no longer a clear interface where current flows below the interface and current does not flow above the interface. Instead, there's a transitional zone where the ethanol water mixture transitions from lower to higher conductivity. This makes it very difficult to detect a water ingress into a tank containing an ethanol fuel blend, because a small ingress of water will only subtly change the conductivity instead of the dramatic change in a tank without ethanol. If there is water ingress and it is not at the bottom of the tank, there may be only a very slight conductivity increase, since all the water may mix with ethanol before it can reach the bottom of the tank. The best thing to take away from all this, of course, is that it's never a good idea to add water to an underground storage tank containing an ethanol blend. As discussed above, it causes problems in detecting water ingress, but worse than that, it mixes with the ethanol from the gasoline and ethanol blend and moves it to the bottom of the tank, which is not desirable because it can change the makeup of the fuel. So due to time constraints, I have limited my presentation to just these two examples, which are challenges concerning ethanol blends, and I have not addressed biodiesel blends. But the reason I have not addressed the biodiesel blends is because there are fewer challenges, as far as functionality challenges, that is, when using release detection equipment and biodiesel blends than the other biofuels, due to the properties of diesel and biodiesel blends being very similar. In fact, B5 is considered the same as diesel and not a biodiesel blend by an ASTM standard. What the NWGLDE disclaimer statement on this slide is saying is that all release detection methods that are to be used with alternative fuels need to be evaluated using those blends. However, in the next slide, you'll see that the workgroup has made some exceptions to this disclaimer for biodiesel and some biodiesel blends as a result of a white paper that was submitted for our review by the Biodiesel Industry Advisory Panel. Right now, there are no exceptions for ethanol and ethanol blends, but that could change. In 2011, Battelle issued a draft white paper entitled Draft Technology Assessment, Suitability of Leak Detection for Use in Ethanol Blended Fuel Service. Battelle used existing literature and experience to determine the expected functionality and applicability of release detection technologies when used to detect releases with ethanol and ethanol blends. Battelle plans to obtain laboratory scale testing and full-scale testing data and use it to finalize the draft technology assessment. Based on the National Workgroup review of the Battelle draft technology assessment, we would expect that our review of the final technology assessment would allow us to add exceptions to this disclaimer statement for the methods of release detection used with ethanol and ethanol blends. As I just discussed, the disclaimer statement on this slide lists exceptions to the disclaimer statement on the previous slide. It basically says that if leak detection equipment is applicable for use with diesel, then it is also applicable for biodiesel B6 through B20 and B100. This exception does not apply to the release detection methods for the biodiesel blends indicated in this disclaimer exception. As already mentioned, this disclaimer statement resulted from our review of a white paper that was submitted to the National Workgroup in 2010. The title of the white paper is Effects of Biodiesel Blends on Leak Detection for Underground Storage Tanks and Lines, and it was written by third-party evaluator Ken Wilcox and Associates for the Biodiesel Industry Advisory Panel. You can find a copy on our website at NWGLDE.org by clicking on Downloads on the left side of the page, and then paging down to where you'll see Alternative Fuels White Papers. The author used reference materials and his knowledge to determine the expected performance of each of the release detection technologies when used to detect releases with biodiesel and different blends of the biodiesel. The conclusion of the white paper is that there are only a few vapor-dependent release detection methods that would need to be evaluated with biodiesel B6 through B20 biodiesel blends and B100. These release detection methods are already known to not work very well with 100% diesel due to its low volatility. So it's no surprise that they would probably not work with biodiesel blends either. There are also a couple of release detection methods that the author of the white paper just wasn't comfortable with as far as being used with biodiesel B100. So his conclusion was that they would probably need to be evaluated in B100 just to be sure. As you can see on the slide, the National Workgroup disclaimer statement includes ASTM standards for biodiesel B6 through B20 and B100. ASTM standards specify that biodiesel be made only from soybeans and therefore does not include what I'm going to call homemade biodiesel, which is usually made from most any kind of animal or vegetable oil. The problem with this homemade biodiesel is that the properties vary so much that it's impossible to categorize them. Since there is no ASTM standard right now for B21 through B99 biodiesel, to limit biodiesel to that which is made from soybeans, the work group decided not to include these biodiesel blends in the disclaimer. The two National Workgroup disclaimer statements shown on previous slides both refer to data sheets. For those of you who are not familiar with the NWGLDE listing data sheets on our website, a portion of an actual data sheet is included on the slide. As you can see on the slide, the applicability section lists different fuels that have been found to be applicable for use with each release detection equipment listing. Like the example data sheet shown on the slide, there are quite a few other release detection data sheets that list biodiesel and biodiesel blends. Our initial policy, after review of the biodiesel white paper, was to require owners to request the addition of biodiesel and biodiesel blends on each data sheet if they believed it fell within the parameters of the white paper. We had quite a few manufacturers request this, and it soon got out of hand, and we discovered that this would become a very tedious task if we were to continue this, since we have over 400 listings on our list. So instead, we quote-unquote listed all of the applicable release detection equipment all at once using the disclaimer statement shown on the previous slide. Therefore, even though you do not see biodiesel in the applicability section of a particular data sheet listing, that does not mean it is not included. And of course, you do need to look at our disclaimer to see how that works. If the release detection equipment listed on our website fits the parameters in the disclaimer shown on the previous slide, then the biodiesel blends are applicable. There will probably be quite a few methods that may be close to being listed by the National Workgroup once a Battelle draft technology assessment is finalized. As I discussed in the previous slide, the Battelle draft technology assessment will most likely allow us to add another disclaimer exception statement that will make ethanol and ethanol blends applicable for use with certain release detection methods in the same way that biodiesel blends were made applicable. Also, one manufacturer submitted a letter to the National Workgroup written by a third-party evaluator justifying the addition of ethanol and ethanol blends to all their automatic and mechanical line leak detector listings. The National Workgroup approved the letter, and ethanol and ethanol blends were added to the applicability section of the listing data sheets. You can see an example on the slide that's up on the screen right now. There are quite a few other automatic and mechanical line leak detectors on the workgroup list where the manufacturer could do the same thing, which would allow their line leak detectors to be listed in a very short period of time, but so far we've had very few do that. I've already discussed most issues preventing biofuels from being listed, so I'm just going to summarize them here. Based on the workgroup review of the biodiesel white paper, there are a few methods of release detection equipment that we agree are not applicable for diesel, and therefore will probably never be able to have biodiesel or biodiesel blends included in the applicability section of the listing. Also, to ensure that homemade biodiesel is not approved for use with release detection equipment, the workgroup will not list biodiesel B21 through B99 on any listing until there is an ASTM standard available. The National Workgroup review of the functionality and applicability discussed for release detection methods in the final Battelle technology assessment will probably indicate that some methods should be listed in our disclaimer as not being acceptable for use with either ethanol or ethanol blends. But that remains to be seen. Other release detection equipment which do not fall into the above categories either already are listed as applicable for some of or all biofuels or have the potential to have all the biofuels indicated as applicable on their workgroup listings. It is left up to the release detection equipment manufacturer as to whether they want to pursue evaluating their equipment to allow biofuels to be added to their listings. And with that, I will let Jacqueline take over and see if there's any questions.
All right, if you have any questions, you can go ahead and put them in the chat. Okay, I'll just give everyone another about 30 seconds here. If you have any questions, you can go ahead and enter them. Okay, thank you, Curt. And again, there will be time at the end of the webinar if anyone has questions that come up for Curt. Okay, thank you. Okay, I'm going to switch over to Anne. Are you there, Anne?
Hello.
Hi.
Hi.
Okay, I'm passing the ball to you, and we have plenty of time, so you won't need to move quickly over anything.
Okay.
And the full screen button is on the left-hand corner and ready for you.
Okay. And I want to get my laser pointer here. Wait.
Okay.
That didn't work. Wait.
The
annotation tools, yeah.
Mm-hmm. And then it's that first arrow on the left, but you want the down arrow next to it, not that big green one.
Okay.
There it is.
There we go. Okay. Okay. Well, thank you, Jacqueline. My name is Anne Marie Gregg. I am from Battelle Memorial Institute. It is a great honor to actually be part of this group. I've spoken with Kevin and Curt many times, and it seems like the more and more we talk about it, the more understanding we gain, and the better off everyone is. But there still are some questions that need to be answered, and ultimately we want to answer that big question as do the leak detection technologies work with the new fuels coming onto the market? And basically, what I've been doing in the lab is looking at the automatic tank gauges, the water detection float specifically, and the water ingress detection specifically, and then looking at the broader categories of leak detection technologies to see how well they may work in the different blends. So today what I'd like to do is kind of go through some of the background. I was going to do that pretty quickly, especially since we got such a great background from Kevin and Curt with the water issue and the ethanol mixing. Then I'd like to give you all the details of the environmental technology verification project that I worked on. Basically, this is where we actually tested 4 different water floats following a quality assurance project plan. And then we've got the observations and results presented within here. And then what are we doing next here? And that's kind of what Curt was talking about with the technology assessment, looking at the broad picture and what's the ultimate end goal here. So basically, this is the whole mixing problem. So this is where you've got your alcohol drink, your water and your ethanol mix, and your water basically is miscible in the ethanol. So will it be able to be detected at the bottom of the tank? I'm not going to go into too many details here. The way we went through this research is that we followed a specific process called the Environmental Technology Verification Process. And this is a voluntary program that basically gathers data in a third-party way, credible data, without comparing or judging anything. Just this is how it was tested, this is the parameter we were testing, and this is the result for it, so that decision makers have the information that they need to make their decisions. And Battelle runs this program under the Advanced Monitoring Systems Center, and we do this through a cooperative agreement with EPA. It's been about 15 years now. We do multiple different kinds of monitoring, detection, sampling, and characterization technologies. And it is this third-party verification process that follows a peer review process. And when we use the word verification, sometimes there's a little confusion about what that means. So I did put that down here. And specifically, when we say verification, we're just saying they went through the process of we collected performance data, and these are the data. We're not certifying, we're not saying that they meet a standard, we're not giving them a stamp of approval, and we're not making any judgments. Okay? So these are the parameters that we looked at, the different metrics that we basically compared everything to. We looked at the sensitivity in 2 different levels, the tolerance limit and the minimum detectable level change. Now both of these are very similar to the original EPA protocol. So technologies, the ATGs, have already gone through this process with the diesel fuel or the gasoline, but mostly diesel, was used for the initial testing. So this is kind of following that same process. We also wanted to look at precision, accuracy, and then any kind of observational information that we could gain, especially with respect to phase separation. We basically organized this test into 2 main tests. The first test is the detection of water with an ingress that's continuous. So the difference between the different portions of this test is that we ingress the water continuously with a splash or without a splash. So when we had a splash, what we wanted to do was just kind of have the water free fall. Say it was coming from the top of the tank and it was just kind of falling into the fuel and going down the fuel column and interacting, you know, as much as it would with this certain splash and kind of mixing around. When you have no splash, what we did was we moved the water delivery tube close to the fill tube so that it actually had a surface that it kind of followed down as it fell and then kind of went through the column along the fill tube and went directly to the bottom. So there wasn't a big splash. There was minimal interaction with the fuel column, but it just kind of followed along the drop tube. The second test was really looking at a catastrophic water ingress, some kind of dump from the spill bucket, something where a lot of water would come in at the same time, maybe some kind of runoff from rainwater or something like that. And what we did was we looked at the water ingress and whether the water was detected as that large ingress, and then what would happen after you got a fuel dump. So that's kind of where the throughput issue kind of comes through that Curt was talking about. This is the vessel that we used. What we wanted to do specifically was perform these tests on a large scale to really see what's going on in tanks and not do it in some kind of small vessel on a bench that may not mimic the way tanks are geometrically and different situations that may just come about because of the scale. So what we did was we used a Xerxes shell that was 6 foot in diameter, and we cut it to about 4 1/4 foot, put glass ends on it, put measuring tape along the outside. You can't see it, but there's actually a little tiny measuring tape on either end built into the resin in the bottom of the tank. This black tube down the center, that's our fill riser, basically. The four posts here, those are our 4 technologies, as you can see. And there's a little bit of moisture here, but the bottom floats are the water floats, and then there's top floats up here as the inventory floats. What we also have up top here is our water delivery system. These here are our risers for the ATGs to be installed. And what we did was, since tanks aren't really flat on the bottom, but we did kind of want to simulate that, and we didn't want to bias any situation. So there is the smallest little bit, it's about 1.5 liters of resin that we put along the bottom to just equal out the bottom slightly. So the technologies would all basically be working from the same ground zero. And I'd like to thank some of our in-kind contribution from BP, Technologies, Xerxes, and Marathon to kind of pull all of this together. This is our water ingress system. It's just really simple. We didn't want to cause any safety hazards with using some different electrical equipment. So we used a gravity system, kind of similar to your toilet, basically, that would feed one head to the other. The water ingress rates we used were about 150 mils to 190 mils a minute. And the placement of the tube, basically, that ingressed the water is how we differentiated between the with or without splash. So the without splash was up next to the fill tube, and the with splash was just kind of hanging out in the headspace of the tank. Jacqueline?
Oh, yep, there you go.
Sorry. Okay. I'm going to go back one more. Uh-oh. Is everyone's screen black?
No, that's we're on the video, that first with splash video.
Oh, shoot.
Are you?
Yeah,
maybe,
I don't
did
see
you
it.
freeze?
Can you see it?
Yeah.
Is
that the slide you want? Did your computer freeze?
I just have a black screen entirely. I have the little NWGLDE monitor box up top right, but that's it.
Okay. Did you try moving to a different slide?
Okay.
Okay.
Okay. So only the file owner can play this media file, is it?
Oh, okay. So that must be me.
Okay.
So do you want me to? Do you want me to play it and then while you talk? Okay. Here,
right,
I'm going to take the.
Okay.
I'm going to take the ball away from you. Sorry.
That's perfectly fine.
Okay. And which one did you want? The with splash or without?
We'll do both.
Okay. All right. This one's the with splash, or I'm sorry, without splash. All right. I'm going to hit play.
Oh. Okay, so it actually should say E15 at 65% level without a splash. And so as you can see, this is where the water is kind of going along the fill tube, as I'd mentioned before, and collecting down at the bottom of the tank. So there is some mixing going along the tube here, but it is generally all getting to the bottom of the tank. Okay, and the next video is with a splash. Again, it's E15, and the water is, starting out at a nice vibrant blue color. The fuel is yellow. As it kind of comes through the fuel column, you can see it spinning around a little bit. It does kind of turn green, give the appearance of green, I guess, and then gets to the bottom and collects. Very similar to the other without splash scenario.
Okay. I'm going to hand the ball back to you.
Great, thank you.
And then you have control again.
Okay, so these are the technologies that we tested. Being the Environmental Technology Center, basically what we do is we talk about technologies in general. So these are the technologies that were tested, but from here on out what I'm going to do is refer to them as technology A, B, C, or D, because we're really not comparing or making any judgments. We're just kind of giving you the overall understanding of the data that we collected. And you certainly have access to all of these publicly available documents to kind of take a specific look at certain things if you're interested. So let's go back to full screen. There we go. So we do have the Vita route, their standard water float, and then the phase 2 water detector. So that's like their standard float that they were using in gasoline, and then their next generation float that they've developed since then. Excuse me, same thing with Franklin Fueling Systems. The difference between the TSP IGF-4 and the TSP IGF-4P is that second generation portion of it. This is the design. So when I was talking about fill heights, this is one of the variables that we controlled. We had two different fill heights, at 25% full and 65% full. We did use 3 different kinds of fuel types. We did an E0, an E15, and an E85. And what you'll see along the top here are the test 1 runs where we have the continual ingress with and without a splash, and then the test 2 runs as being dumps. So the highlighted squares in yellow here are the examples that I'll be going through over the next couple slides here. Kind of give you an idea. If you do look at the E85 line here, we did not conduct the 65% full level with those tests, because what we did find in the 25% level is that our tests were basically inconclusive. So we would run a test where we would expect the technology to alarm within an hour, maybe an hour and a half. So that's how we set up our flow rates. That's how we kind of set up things, given information that we had from the vendors. And then we basically decided a test would be over in 3 hours. So if it was expected to alarm at 1, and if it didn't alarm 2 hours later, then we basically aborted the test, which is what happened with the E85. So our testing observations with the E0, as you'll notice, the fuel was very yellow. There wasn't much mixing, and it's fairly clear to see here at the bottom that the water is separated and that the floats are floating on top. See? This is what the data look like when you graph from the ATG box. So the black line is giving the observed heights, basically from what we read, and then all the different lines were the 4 different technologies. You'll notice that the technologies are reading very in parallel and in line with the way the water is actually ingressing into the tank. You'll see that they generally detected, so we had to wait till all of them detected before we could go to the next step. So they all detected relatively at different times, but then once they detected, they really followed the line as the water was incrementally ingressed. So what I'd also like to kind of point out at this point is that these are detecting at different points because of how they were installed in the tank. And this is going to be an issue in the field, and actually what we tried to do is minimize this by adding that resin onto the bottom of the tank, like I said, but ultimately when they were installed, they still were installed, just above the tank, especially these last 2. So a lot of times tanks have debris or sludge, or maybe they don't at the time of installation, but they know that it's going to happen over the next couple of years or something like that. So there's this space kind of built in before that it's not actually sitting directly on the bottom of the tank. And that would actually help with what we saw in the pictures from Kevin, where there's a lot of deposits and things on the floats, that if it's actually a little bit above the bottom of the tank, that it's not going to be as affected by those different kinds of fouling issues. So the bottom 2 technologies here were basically installed just a smidge higher than these other ones that were actually a little more in line with what we saw. So this is an E15. This is basically the same thing. We were at water ingressing, and again, the technologies all kind of alarmed at different rates, at different times, I guess. What you'll see here now is that all the technologies are generally reading a lot lower than what we are reading. Now that could be because we were using our eye, and as you have this, there's not as much of a clear separation as there was with the E0, and we definitely acknowledge that. But I'd also kind of want to recognize that they're generally all reading lower than what we would actually see as this water ingress. So would the water be detected? It's kind of more of a conservative, alarming situation here. And you'll also see that the parallel lines, as the incremental test goes forward, they don't necessarily stay as parallel as they were before. So there does seem to be some kind of change in the performance when it comes to the E0 versus the E15. This is an E85 test that I was telling you about. Basically, it went on for about 3 hours. this 9:45, this was about an hour after the first test. So when we were ingressing this was a without a splash. So it came down the bottom and it just kind of swirled around and ended up making this green hazy portion. And then we still have this yellow portion here that's probably about 8 inches or so. An hour later, we're getting a more deep green, and then we're down to about, I don't know, 1.5 inches or 2 inches of this yellow top phase. About 40 minutes later, we've got a fraction of an inch of this yellow phase and everything else is green. So as you can see, there's quite a bit of water in this system, but the water's not being detected because it's not at the bottom of the tank. This is the computer readout of what the technology saw. Basically, they all kind of are down here, all 4 of them, and then these 2 kind of jump up, but basically it's not a reality. So this one here pegs out at about 5.5 inches, and so that's as high as it would ever go. And this one here pegged out at 13 inches. So this ended up underneath the fuel float, because at 25% full, it was about 17 inches in height entirety. Moving on to the dump tests. So this is kind of where we might need to bounce back and forth, Jacqueline, so I don't know if you want to just move through the slides for me at this point because of the videos. But basically, this is what we had as an output for the technologies during the dump test with E0. So we have 0 water. We dump the water, the first dump of water, about 2 gallons. One of the technologies responds. We wait for it to kind of equilibrate. We do another dump so that the next technology gets to the point where it would alarm. And then we let it kind of calm down. Here's where we start our fuel dump. So this is, really expected because it's turbulent during the fuel delivery time, and then it calms down again. So basically the water is detected before the fuel dump and the water is detected after the fuel dump. And that's exactly what we would want to do because the water's still in there. And Jacqueline?
Okay, I'm going to take the ball away from you. And I'm going to hit play.
Okay. So this is an up-close look at the tank bottom, and the water is going to come in. There it goes. There seems to be a delay on my computer. Yeah, it seems kind of pixely to me. I hope it looks a little better for everyone else. But you can look at it some other time when it's not coming through the webinar, and it probably would be a lot clearer for you. So you'll see at the bottom, it says the E0 dump. The bottom is blue, and basically the fuel looks a little hazy right now, but it becomes a nice clear fuel again. So the water is nice and separated. Okay, next.
Okay.
The E15 dump, what you'll see here is the initial water dumps. Both the technologies went at the same time with this one. And when we started the fuel dump, what happened was the water float technologies kind of, were startled by the turbulence and then went straight down to the bottom of the tank and didn't move for the rest of the test. So the water was detected after the water was dumped, and the water was detected before the fuel dump, but then the water was not detected after the fuel dump. Okay? And I've got a video of that, and that's kind of not as close up to kind of give you a better perspective of the tank. And there's a lot of buffering going on with mine, I think.
There, it just came on mine, the dump. And again, I will post all of these online. It takes about 2 weeks for our webmaster to get things posted, so check back towards the end of the month and these videos will be posted so you can see them.
This is okay. This isn't really working. Okay. So what's ultimately important is that after you get that fuel drop, the water was detected, you have your fuel drop, and then basically this is what we observed. So it looks like the E85 kind of run, basically. So we end up with this hazy green down here and kind of a denser phase on top of more fuel here. So there's clearly a lot of mixing going on, and then you can also very clearly see the floats at the bottom of the tank. All right, the E85 dump test did the same, did pretty much the same thing as the ingress tests. It was very inconclusive. The water came in, and it was very dark. Some actual water ended up at the bottom of the tank, and then most of the water ended up into the top portion, and it was nice and green. So one of the most of the technologies did nothing in this situation. This one, technology B, actually did go up and then go up and then go up again, and this is where it ended up at the top of the fuel float, or at the bottom of the fuel float. So you had a float on top of a float in this situation, looking at it being 40 inches. So it just kind of ended up what we called neutrally buoyant at different points throughout the fuel start.
Do you want to run the next video? I'll go ahead and, yeah, okay. Just in case anyone is able to see it.
I think that last one was probably the longest. So it's greener on top. It's very dark blue on the bottom. So there is some kind of phase separation there. May not be a true phase separation. It's just kind of like the mixing. And then when we definitely add more E85, the higher ethanol, then all of that gets entrained in the fuel, and it becomes pretty much solid green color.
Okay, I'm going to pass the ball back to you. All right.
Okay. Okay, so this is what it looks like at the end of the fuel dump after the E85 had all the water in it. So it ended up being a very solid green. This is a summary of the results of the different parameters that we looked at. The tolerance limit and the minimal level change. Like I said, this tolerance limit is where the technology was installed to be able to detect. So the first two technologies were very similar, a little over ½ an inch off of the bottom. The other two technologies were actually installed slightly higher than the others, but their 0 point was set at at the point where they were set, hanging in the tank. So one technology hangs on a chain and the other technology is on a rod. So there's just little variations when it comes to the actual installation and where it will actually be zeroed out and the way that it's actually performing. So technology C&D actually measured the water where it was at 0 point, basically, but the 0 point was they were actually installed higher in the tank than technologies A and B. So you saw that literally they were all responding within the same few minutes in those previous slides. So as far as differences in that, it's kind of difficult to see with these numbers. Get my pointer back again. So the minimum level change, the regulation says that we need to be able to measure 1/8 of an inch difference. So all of these are measuring with 1/8 of an inch. These are at 1/16. This one's at 1/8. And that was the design for that portion of the test. The precision, that basically is really driven by the standard deviation. So we were looking at all of the runs together and how much standard deviation we had. So technology A actually had the smallest deviation of all of the measurements that it took. So it was a little more reliable in that sense. And then technology B had a little more variation, but it was a little different. And then C and D were very similar in its performance with its precision. The bias, we have to recognize with the bias that we were using our eyes to measure. Even though the measuring stick was stuck in the tank and wasn't moving, there were different people making that measurement, and we tried to do as much as we can to make that measurement as consistent as possible. But ultimately, you'll see a general trend that there's a negative bias, which was shown in the previous slide with the E15 and how it was underestimating what the water was that we were actually visualizing in the tank. So what I'd also like to point out here is that these data are only the E0 and E15 ingress runs, and they are all combined as well. So what I'd like to do with the technology assessment is really tease apart the data between the E0 and the E15 data and try to really understand the different parameters that had more of effect or less of effect in its ability to detect the water. So our overall conclusions. Basically, the regulation states that water detection technologies should detect water at the bottom of the tank, but it doesn't address anything that's entrained in the fuel because of this ethanol issue. So there's definitely something that needs to be addressed in the regulation. The water sensors that we tested did not detect the water in the test vessel containing either E15 or E85 blends, and that was because of the water being entrained in the tank, into the fuel. So it wasn't at the bottom of the tank. There is sufficient data, or basically, ultimately, there is not sufficient data to evaluate whether these technologies would indicate a potential release under every circumstance. And when we say every circumstance, well, we can't cover absolutely every circumstance, but the circumstance where you're measuring water and then you get a fuel dump that happens every week, multiple times a week, multiple times a month, however your throughput is, and you get a fuel dump and then you don't have the water anymore. So that's a very common circumstance where the situation could happen. So you may have a situation where you have water ingress, but it never actually gets detected because you have the throughput that basically keeps that water entrained. And if you would like to see the reports, the verification statements, this is the link to all of those files. It is on the EPA website, and basically the reports have all of the data in it. Everything you'd want to know about it, all the QC reports, everything in it. The verification statements are about 4 to 6 pages, and they are a summary of the test design and the results, and it's specific to each technology. So there's 4 different verification statements, and then there's 2 large reports, and those are done by the different vendors. So ultimately, what do we want to do is ask this question do UST leak detection technologies work in ethanol blended fuels? We went a long way with that in trying to understand what's going on a large scale with water detection floats, with one of the most popular detection systems used out there. And then what we also did was write this technology assessment paper. So currently, it's just kind of pulling together ideas and assumptions and you know, minimal data. But as we revise it, what we want to do is incorporate the ETV data and then incorporate any data that we collect over the next year in our laboratories, and then any other data that we can collect that would support that that's out there in the published literature. So basically, people who are making these decisions, the National Work Group, government regulators, federal, state, anybody, can have this information to be able to kind of point to and say, okay, I can understand it working this way or that way. And basically, the National Work Group specifically will use this paper similarly to the way they use the biofuels paper, or the biodiesel paper that Curt was talking about, that Ken Wilcox Associates wrote a little while ago. So hopefully this tech assessment will really really gain and, you know, pull together a lot of the information that's not necessarily all pulled together into a nice package right now. So what we'd like to do is, at this point, what we're doing is writing a QAP. We are looking at 3 different phases of testing, and we'll be collecting these data over the next 6 months or so. The first part is to look at the fuel properties and the mixing behaviors. So we want to look at multiple different ethanol blends and a couple of different properties that are particular to leak detection technologies. We'd also like to look at the performance of the technologies on a laboratory scale. So it's really not feasible to do what we did on that large test vessel a lot, or even, again, who knows, it would be nice to use it again. However, what we need to do is be able to test water ingress on a laboratory scale so that we're not wasting thousands of gallons of fuel because we're adding water to it. That's a huge expense. So what we want to do is scale down what we did on the ETV scale down to a laboratory level where we're going to produce a lot less waste, but basically show the continuity between the data collected and understand the scaling factor. And then finally, what we'd like to do is some field demonstrations. So operate the different technologies in real-world conditions, and then simulate leaks at different rates and see how long it takes them to detect, when they detect, and ultimately this would be focused on actual leak detection and not specifically the water ingress portion. So if anyone would be interested in knowing more about that particular part of the project or have any technologies or sites that may be good sites for us to do some research on, I would encourage you to get in touch with me. We would like any kind of in-kind contributions possible. Basically, I would like to acknowledge a laundry list of people who are part of this first part of the project and actually are continuing on. We've gotten the research funding from the EPA Office of Underground Storage Tanks and the Office of Research and Development. The National Work Group has been very involved from every step of the way, looking over all of our documents, making sure that what we're doing is making sense. We've got peer reviewers looking at all of our documents, Sam Gorgie and Randy Jennings. And then those are switching out for different documents that we're still producing, basically. And this is from a group that's actually the Underground Storage Tank Leak Detection Stakeholder Group. And we've been meeting over the last year to kind of pull together the final parts of this research and what data gaps there are and how we really should move forward. The vendors, of course, Feeder Root and Franklin Fueling Systems, and then our in-kind contributors, as I've already mentioned, BP, Technology, Marathon, and Xerxes. So, does anyone have any questions?
While you're typing in questions for Anne, I actually had a question come in for Curt, so I'm going to unmute Curt as soon as I find him. Okay. You there, Curt?
I'm still here.
Okay. I had a question from Carrie. Is it true that the Feeder Root water probe is only certified for up to 20% ethanol? If so, is there any water probe that will detect water in E85?
I don't think, to my knowledge, I don't think Veeder-Root has evaluated their water sensor that was that I referred to. Well, one of them that I referred to, not by name, of course, but they have not evaluated that water sensor at all. So that was the first part of the question. Now, repeat the second part again now, if you would.
Is there any? Yep. Is there any water probe that will detect water in E85?
Not that's been evaluated. To my knowledge, we don't have any evaluations in that where anyone evaluated a water sensor that would detect water in E85.
Okay. Okay, and I have a question from you from Annette. What percentage of water was added to the tank during the test?
Hi, Annette. So I don't have those calculations, but we can actually do that, and that was what I was going to do for this teasing out of the E0 and E15 portion. It was lower than what would cause phase separation. So if we were at about 200 mils a minute, I think we calculated it would take at least 2 gallons to do phase separation, and that was really why we decided to dump 2 gallons during our dump tests. So that's a good question, but I don't have a specific answer for you.
Okay, we have a question from Daryl. I'm going to unmute you. You there, Daryl? You there? All right, I will ask this question for him. Would you expect similar results given a slow groundwater ingress from the bottom of the UST?
So the reason we did a higher rate of ingress is because we wanted to control the amount of time it took for the testing. I would imagine that if you do not have any disturbances in the tank, as far as a fuel dump, that yes, the water would accumulate at a much slower rate, but it would still accumulate. And depending on the head pressure and whatnot of the water table, clearly too.
Okay, go ahead, everybody, and use that chat function to enter questions. We will take questions for all speakers. If you are on a headset and do not have a microphone, if you could just let us know who the question is for. Also, if you are participating in a group today and you have not typed into the chat to let me know how many people are watching with you, if you could go ahead and do that now. I counted at least 3 groups I hadn't heard from yet, so if you haven't done that, please do that now. Okay, I've got a question for Kevin, so I'm actually going to unmute all of our speakers now. Okay, this question is from Tim for Kevin. Hold on, let me expand my thing here. In cases where we see extensive corrosion in the STP sump, but see no product collecting in the sump bottom, what can we generally presume is happening? If ethanol vapor is likely the case, what should we consider to be the likely direct source of the vapor?
Question from Tim. Is this Tim Smith by chance?
Nope, Tim Doheny, and I apologize if I pronounced your name wrong.
Okay, I was just curious, but that's a good question, and I think what's happening in the majority of cases are these components that are in these STP sumps that routinely contain product. They're under considerable pressure, internal pressure, and they all have various kinds of elastomeric seals and gaskets in them that we rely on. And so I think what we're seeing are essentially most of these systems, and I'm not being critical, it's just the nature of the beast. Most of these systems are not actually vapor tight. While we may occasionally get some, and obviously it's possible to do that, I think, and it's just my opinion, that most of these are not vapor tight. So we have a rather steady supply of vapors within all of these sumps, or virtually all of them, at one point in time or the other. So I think that's really what we're dealing with. Don't see liquid leaks, but it is a small, very small leak, whether it's just occurring through permeation of these elastomers or whatever that is happening. I think we are subject to seeing vapor leaks in almost all of these systems.
Okay, I have a question for Ann from Robert. Robert, are you there?
Yes, I'm here. And not the dump test, but the other test, at what rate did you add the water to the tanks?
At about 150 mils a minute.
And
again, the way we calculated that was so that we would elicit a response from the technology within an hour.
Okay.
So we weren't waiting, we weren't allowed to hold fuel in the tank overnight. So we really had to restrict what we were allowed to do in a certain amount of time, and basically increase the rate of the water coming in, because that's, that's just waiting time.
And so, Ann, can I ask you a question? This is Kevin. That 150 mils per minute, to put it in terms we can better relate to, that would be equivalent to a little bit less than 3 gallons per hour. Would that be right?
Well, it's about 1/10 of a liter.
Yeah, the relationship I'm making is that when we test an automatic line leak detector, that is 189 milliliters per minute is equivalent to 3 gallons per hour. So
yeah, it's much higher than the 0.2 gallon an hour.
Yeah, so it's about 2.5, a little more than 2.5, somewhere between 2.5 and 3 gallons per hour.
If there are any more questions, go ahead and enter them in the chat. I'm going to wait about maybe 30 seconds here, so if you have one, get one in. I will be sending out an email as soon as we're done here to all of the participants who registered and signed up with their email. This email will contain a link to an online evaluation. It will also have all 4 of our speakers' email addresses in case you have any follow-up questions. Oh, we have one for Curt. What test method can be used for B75?
B75? Okay. Well, we have excluded everything between B21 and B99 because there was no ASTM standard for the manufacture of that biodiesel, and therefore it allows any kind of homemade diesel. It could allow any kind of homemade diesel to be considered. So we've excluded any listings for B21 to B99. Did that answer the question?
Yes. Yep. Okay, and we have another question in for Ann from Brad. Did you monitor the water bottoms in the E15 blend to see if they would, in quotes, go away on their own over time, or did they remain constant without a fuel delivery?
Well, there was time between where we waited after the water was dumped in before we actually had the fuel dumped in. So, there was definitely that leveling off. I don't know if I can go back to that slide.
Oh, hold on. Let me pass you over the ball real quick. Okay, go ahead.
Oh.
That's the E0 video. There you go.
Okay, so basically what we were saying is you were wondering at this point, is that what you're saying, Brad?
Did you monitor the water bottoms in the E15 blend to see if they would go away on their own over time, or did they remain constant without a fuel delivery?
Yeah, so they remained constant as long as there wasn't a disturbance here. So this was a good half an hour before we started the fuel dump, where it was pretty steady, and they were measuring that water.
Could I follow up with that question, Ann? This is Kevin
Sure.
again. You guys did not make any attempt to simulate like an STP motor running in a tank like it would in the real world, did you? It's just sitting there absolutely still, right?
Right.
Okay.
So, I mean, the technologies have certain parameters when they're installed. They need to be so far away from an STP so that they're not influenced by that kind of agitation. And that's a really good question, whether that distance would need to be different in an ethanol blend or not, or whether that would really even make a difference. It's a good thought. I think under this circumstance, we were assuming that there wouldn't be that, but we did not simulate that at all.
Okay, that was the last question that I had come in. I want to thank Michael, Kevin, Curt, and Ann again for volunteering their time to talk to us today. And thank you for all of our participants who logged in. Again, this is the first in a series, so we have at least two more webinars coming up on biofuels. We'll be looking at corrosion in one of the webinars, and we'll be looking at resources in another webinar. And actually, before we go, we have one more question from Joe. Why was E15 used and not E10?
E15 was used. We actually did have E10 on the docket, and given time and resources, what we needed to do was pick one. And we knew that the E15 was coming onto the market, and as far as the data that we'd collected so far, we hadn't seen anything that would indicate that E15 and E10 are very different in their properties. So we decided that E15 was a more severe case than E10 and chose that one.
All right. Thank you again, everyone, and hopefully we will see all of you on the next webinar. Bye-bye.
Okay, thank you, everyone.
Thanks.